Drop something, anything nearby, a pen, your phone, whatever. It falls down toward the earth. Why? 300 years ago, Isaac Newton said gravity pulls it, an invisible force reaching across space, pulling objects together, a force that acts instantly across any distance through the vacuum of space. 200 years later, Albert Einstein said there is no pull. Nothing reaches across space. Gravity isn't a force at all. So who's right? Both, and neither. Because the question, what is gravity, turns out to be far more subtle than asking what pulls things down. It's a question about the nature of space itself, about time, about the fabric of reality. Here's what's really happening. In Newton's universe, space and time were absolute, fixed, unchanging, eternal. Space was like an empty stage, a three-dimensional grid stretching infinitely in all directions, where events unfold. Time ticked forward at the same rate everywhere, for everyone, forever. This was the foundation of physics for 2 centuries. Space as a container, time as a clock, both independent of the matter and energy within them. And between objects, between the earth and the moon, between the sun and planets, between your hand and the ground, there existed a force, gravity. Newton gave us an equation in 1687. Beautiful, simple, powerful. The force between 2 objects depends on their masses multiplied together, divided by the square of the distance between them. A universal constant, G, sets the strength. And it worked spectacularly. It predicted planetary orbits with stunning accuracy, explained ocean tides, calculated exactly when a dropped object would hit the ground, how fast it would be moving, where it would land. We still use Newton's equations today to launch satellites, to navigate spacecraft across the solar system, for almost every calculation involving gravity near Earth. Engineers don't use Einstein's equations to build bridges. They use Newton's, because for everyday purposes, Newton's gravity is accurate enough and far simpler. So what's the problem? Well, Newton knew there was a problem. He admitted it himself. It bothered him deeply. He wrote in a letter in 1692, that one body may act upon another at a distance through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has any competent faculty of thinking can ever fall into it. Read that again. Newton himself called his own theory absurd. Newton gave us the equation that describes how gravity works, but he couldn't explain what it is. He couldn't explain the mechanism. And he knew that was a fundamental problem. Think about it this way. The sun is 93 million miles away from Earth. That's 150 million kilometers. Between us is mostly nothing. Empty space, a vacuum, no air, no medium, nothing physical connecting the 2 bodies. Yet the sun somehow reaches across that emptiness and pulls on Earth, keeps us in orbit, changes our velocity every single second as we curve around it at 30 kilometers per second. How? If there's nothing between the sun and Earth, how does the sun know Earth is there? How does the force get transmitted across 93 million miles of nothingness? How long does it take? Does the force travel, or does it act instantly? Newton had no answer. We've seen this problem before with magnetism, with electricity. Forces that seem to act across empty space without physical contact. We resolved those with fields, electromagnetic fields filling space, virtual photons carrying the force between charged particles. But gravity is different. First, it's universal. Everything with mass creates gravity. Everything, every atom, every particle, every object. There are no exceptions. You can't shield yourself from gravity. You can't turn it off. Second, it's always attractive. Unlike electromagnetism, where like charges repel and opposite charges attract, gravity only pulls. Mass attracts mass, always. There's no negative mass pushing things apart. Third, and this is crucial, it's incredibly weak. Electromagnetism is 10 to the 36 times stronger than gravity. That's a 1 followed by 36 zeros. A trillion times stronger. A small refrigerator magnet, barely the size of your thumb, can overcome the gravitational pull of the entire planet Earth, all 6 trillion kilograms of it, to lift a paper clip off a table. Think about that. the entire planet pulling down on that paperclip, and a tiny magnet wins. So if gravity is so weak, so universal, and acts across empty space without any known mechanism, what is it? That's what Einstein asked himself in 1907. And the answer he found over the next 8 years changed everything we thought we knew about space, time, and reality itself. Einstein started with a simple observation. Actually, it was more than an observation. It was a thought experiment. A Gedanken, he called it. Imagine you're in an elevator, a closed box, no windows. You can't see outside. You have no way of knowing where you are or what's happening beyond the walls. Scenario 1. The elevator is sitting still on Earth. You feel your weight pressing down on the floor. You feel normal. That's gravity, you think. The Earth pulling you downward with a force equal to your mass times 9.8 meters per second squared. Scenario 2. The elevator is in deep space, far from any planet, far from any star, floating in the void. But it's not stationary. It's accelerating upward at exactly 9.8 meters per second squared. The same acceleration as Earth's gravity at the surface. You'd feel exactly the same. Your feet pressing against the floor with the same force. Objects falling when you drop them, accelerating downward at 9.8 meters per second squared. Your body feeling weight, pressure, the sensation of standing, everything behaving exactly as if you were on Earth. Einstein realized there's no experiment you can do inside that box to tell the difference. No measurement, no observation, nothing. Being in a gravitational field is physically identical to being in an accelerating reference frame. He called this the equivalence principle. Gravity and acceleration are equivalent, indistinguishable, two descriptions of the same physical situation. This was 1907. It would take him another 8 years to work out what it meant. But here's where it gets strange. Shine a beam of light across that accelerating elevator, from one wall to the opposite wall. By the time the light reaches the other side, the elevator has accelerated upward. The floor is now higher than it was when the light started its journey. From inside the elevator, the light appears to curve downward. It doesn't travel in a straight line. It bends. Now, if gravity and acceleration are truly equivalent, if there's no experiment that can distinguish between them, then light should also curve in a gravitational field. Not because gravity pulls on the light. Light has no mass. There's nothing for gravity to pull on, at least not in Newton's theory, but because something else is happening. Einstein realized mass doesn't pull on other objects. Mass doesn't reach across space and exert a force. Mass curves space and time themselves. This took years to work out. The mathematics was brutal. Einstein wasn't a mathematician by training. He struggled. He made mistakes. He had to learn entire new branches of mathematics, differential geometry, tensor calculus, concepts that hadn't even been fully developed yet. But by 1915, he had it. Space and time aren't separate things. They're not independent. They're woven together into a single four-dimensional fabric called spacetime. 3 dimensions of space, 1 dimension of time, unified. And this fabric isn't rigid. It's not the unchanging stage Newton imagined. It's dynamic, flexible, curved. A massive object, the Earth, the sun, a black hole, curves the fabric of space-time around it, like placing a bowling ball on a stretched rubber sheet. The sheet bends, curves, warps around the mass, and objects moving through that curved space-time naturally follow curved paths, not because something is pulling them, not because a force is acting on them from a distance, but because the geometry of space itself is curved. They're moving in straight lines through curved space, the straightest possible path through curved geometry. We call these paths geodesics. It's like rolling a ball on a curved surface. The ball follows the curves not because a force is pulling it sideways, but because the surface itself is curved. The ball is just rolling straight ahead, but straight ahead on a curved surface is itself a curved path. Gravity isn't a force, it's geometry. The Earth doesn't orbit the sun because the sun is pulling on it. The Earth orbits the sun because the sun curves space-time, and the Earth is moving along the straightest possible path through that curved space-time. You fall toward the Earth not because the Earth pulls you down. You fall because the Earth curves space-time, and falling is the natural motion through that curved geometry. So how do we know Einstein was right? How do we know this isn't just beautiful mathematics with no connection to reality? The first clue came from Mercury. Mercury is the closest planet to the Sunday. It orbits in 88 Earth days, moving at 47 kilometers per second, whipping around the Sun in a tight elliptical path. But Mercury's orbit doesn't quite match Newton's predictions. The ellipse itself rotates slowly over time. The point of closest approach, the perihelion, shifts by a tiny amount each orbit. This is called precession. Most of this precession can be explained by the gravitational influence of other planets tugging on Mercury. Venus, Earth, Jupiter, all pulling slightly, perturbing the orbit. But there's a discrepancy. After accounting for all known influences, Mercury's orbit still precesses by 43 arcseconds per century more than Newton's equations predict. 43 arcseconds. That's 43 sixtieths of a 60th of a degree per century. Tiny, almost nothing. For 200 years, this was a mystery. Astronomers proposed solutions. Maybe there's another planet closer to the Sun, Vulcan, perturbing Mercury's orbit. Searches were conducted. Nothing was found. Maybe Newton's law needs a tiny correction at short distances. Maybe gravity isn't exactly inverse square. Maybe. Then Einstein published his general theory of relativity in November 1915. He applied his equations to Mercury's orbit. No adjustments, no fudge factors, no new planets. Just the curvature of space-time near the Sunday. The equations predicted an extra precession of 43 arcseconds per century, exactly. Einstein later said this was the most thrilling moment of his life. His theory explained a 200-year-old mystery without adding anything new. Just geometry. But that was just the beginning. In 1919, 4 years later, came the definitive test. Einstein had predicted that starlight passing near the Sun should bend, curve around the Sun, not because of any force, but because the Sun curves space-time, and light follows geodesics through that curved space-time. He exactly how much the light should bend. 1.75 arcseconds for light grazing the Sun's surface. But there's a problem. You can't see stars near the Sunday. The Sun is too bright. It overwhelms everything, unless there's a total solar eclipse. On the 29th of May 1919, there was a total solar eclipse visible from the island of Principe off the coast of West Africa and from Sobral in Brazil. British astronomer Arthur Eddington led expeditions to both locations. The goal: photograph stars near the Sun during the eclipse. Then compare their positions to photographs taken when the Sun wasn't there 6 months later. If Einstein was right, the stars would appear shifted, the light bent by the Sun's curved space-time. If Einstein was wrong, if Newton was right, the stars would be in their normal positions. Light from distant stars wouldn't be affected by the Sunday. The weather was terrible. Clouds threatened to ruin everything. But during totality, the clouds parted just enough. The photographs were taken. Eddington returned to England. The analysis took months, measuring tiny shifts in star positions on photographic plates, accounting for distortions, uncertainties, instrumental errors. In November 1919, the results were announced to the Royal Society in London. The light had bent, not by the Newtonian prediction, by Einstein's prediction, 1.75 arcseconds. Space-time is real, and massive objects curve it. The headlines the next day made Einstein a global celebrity. Revolution in science, new theory of the universe, Newton's ideas overthrown. Today, we see this everywhere. Gravitational lensing, light from distant galaxies bending around massive galaxy clusters, creating multiple distorted images, arcs, Einstein rings. The Hubble Space Telescope has photographed thousands of examples. We use gravitational lensing as a tool now to map dark matter, invisible mass that curves space-time without emitting light, to find distant galaxies magnified by the lens of foreground clusters, to discover planets around other stars through micro-lensing events. Even more practical, GPS satellites. Remember time dilation? How time runs at different rates in different gravitational fields? This isn't science fiction. It's engineering reality. GPS satellites orbit 20,000 kilometers above Earth. At that altitude, Earth's gravitational field is weaker. Space-time is less curved. Time runs faster compared to clocks on the surface by about 45 microseconds per day due to gravitational time dilation. But the satellites are also moving at 14,000 kilometers per hour relative to the surface. This causes time to run slower by about 7 microseconds per day due to special relativistic time dilation. The net effect, clocks on GPS satellites run 38 microseconds per day faster than clocks on Earth. 38 microseconds doesn't sound like much. But light travels 30 centimeters in 1 nanosecond, 1,000th of a microsecond. In 38 microseconds, light travels 11 kilometers. If we didn't account for this curvature of space-time, GPS would drift by several kilometers per day. Your phone would think you're on the wrong street. Navigation would be useless. Your phone knows where you are within a few meters because engineers understand that gravity is curved space-time, and they program that understanding into the satellites. So if gravity isn't a force, why does it feel like one? Why do you feel weight when you stand? Why do objects fall when you drop them? Why does it seem so obvious that the Earth is pulling you downward? Here's the strange part. When you're falling freely, truly falling, not resisting, not holding on to anything, you feel nothing. Astronauts in the International Space Station aren't weightless because there's no gravity up there. That's a common misconception. Earth's gravity at an altitude of 400 kilometers, where the ISS orbits, is still about 90% as strong as on the surface. They feel weightless because they're falling continuously, freely following the geodesic, the natural path through curved space-time. The ISS is falling around the Earth, and the astronauts are falling with it. No force acts on them from their perspective. They're in free fall, and free fall feels like floating. What you feel is weight. The sensation of your feet pressing against the floor right now is actually the ground pushing up on you. Think about that for a moment. You're trying to follow your natural path through space-time. That path curves toward the center of Earth. You're trying to follow your geodesic, but the ground is in the way. It's solid. Electromagnetic forces between atoms prevent you from passing through. The ground pushes up on your feet with a force equal to your mass times 9.8 meters per second squared. That upward push is what you feel as weight. If you had an accelerometer right now, a device that measures acceleration, it would show you're accelerating upward at 9.8 meters per second squared. Not downward, upward. This seems insane. You're standing still. How can you be accelerating? From the perspective of curved space-time, you're not standing still. You're being continuously accelerated away from your natural freefall path by the ground beneath your feet. Freefall is the natural state. Zero acceleration, floating, weightless. Standing on the ground is accelerating. You feel weight because you're being pushed, not because you're being pulled. Gravity doesn't pull. The ground pushes. And what we call gravitational force is the result of living in curved space-time while being prevented from following its natural geometry. This is why Einstein said gravity isn't a force. In his theory, there's no gravitational force acting on freely falling objects. They're simply moving along geodesics. Only when something prevents that natural motion, like the ground beneath your feet, do you feel a force. Einstein gave us a beautiful description of gravity, space-time curvature, explained with mathematical precision through 10 coupled nonlinear partial differential equations called the Einstein field equations. They relate the curvature of space-time to the distribution of matter and energy. It works spectacularly. Every prediction has been confirmed. But there's a problem, a deep problem, one that physicists have struggled with for nearly a century. General relativity, Einstein's theory of gravity, describes the universe at large scales. Planets, stars, galaxies, black holes, the expansion of the universe itself. Quantum mechanics describes the universe at tiny scales, atoms, particles, fields, the interactions between fundamental forces. Both theories are astonishingly successful. Both have been tested to incredible precision. Both are cornerstones of modern physics, and they don't fit together. When you try to combine them, when you try to describe gravity at quantum scales, the mathematics breaks down. You get infinities, nonsensical predictions, probabilities greater than one, energies that diverge to infinity. At the center of a black hole, Both theories are needed. Extreme gravity in a tiny space. But we have no idea what happens there. The equations give infinity, the singularity, a point where our understanding fails. At the moment of the Big Bang, same problem. The entire universe compressed to quantum scales. Space-time itself curved infinitely. What happened in the first fraction of a second? We don't know. We need a theory of quantum gravity, a theory that combines general relativity and quantum mechanics into a single coherent framework. Physicists have proposed ideas. String theory, where particles are tiny vibrating strings in 10 or 11 dimensions. Loop quantum gravity, where space-time itself is quantized into discrete chunks. Others, but we have no experimental evidence for any of them. No way to test them. The energy scales where quantum gravity becomes important are far beyond anything we can reach in particle accelerators. So when you drop something and watch it fall, we understand it's following a geodesic through curved space-time. We can calculate exactly when and where it will land. We can predict the orbit of planets billions of years into the future. We can design GPS satellites that account for relativistic time dilation. But why does mass curve space-time? What is space-time at its deepest level? Is it continuous or discrete? How does gravity connect to the quantum world? Why is gravity so much weaker than the other forces? Those questions we still can't answer. Newton gave us equations that describe how things fall. Einstein showed us why. The geometry of reality itself. So the next time you drop something, remember it's not falling down. It's following the shortest path through curved space-time, moving in a straight line through a curved universe. And you, standing here, feeling weight beneath your feet, you're not at rest. You're being continuously accelerated away from your natural path through space-time by the ground pushing up on you. Gravity isn't a force, it's the shape of reality. And we're still learning what that really means.